Select the major product or products of the following reaction. So if we look at what we're given in this reaction, our starting material is an alcohol, and specifically because the alpha carbon has bonds to two other carbon atoms, this is a secondary alcohol. And we are reacting this with phosphorus tribromide. So this is the structure of phosphorus tribromide. And we are also using pyridine, and this is pyridine. So pyridine is aromatic, so it's got a structure that looks a lot like a benzene ring, and we have a nitrogen in here. So this is pyridine. And what pyridine is it's a base, but it's not a very good nucleophile. So we would say that this is a non-nucleophilic base. So that means it's not going to try to attack any electrophiles, but if there are acidic hydrogens that need to be removed, then it will do that. Okay, so our alcohol has lone pairs of electrons on the oxygen, and those lone pairs mean it can react as either a base or as a nucleophile. And so on this phosphorus tribromide, that phosphorus is actually a little bit electrophilic. And we've got bromines on there that can act as a good leaving group. So I'm going to draw down here at the bottom. I'm going to redraw this secondary alcohol with its lone pairs of electrons. And I'm going to draw the phosphorus tribromide. So we're going to draw the phosphorus with 3 bromines. Okay, and we are starting with a chiral alcohol, so that's a hint that we want to pay attention to how this reaction is occurring and what the effects are on the stereochemistry of that carbon. So what's going to happen in the first step is the lone pairs of electron on the oxygen are nucleophilic, and this phosphorus is electrophilic. So your alcohol is going to do an SN2 attack on that phosphorus. So you're going to kick off a bromine, leading to this first intermediate. Right, so we still have 2 bromines on the phosphorus. We still have a hydrogen, and that is a fairly acidic hydrogen being attached to oxygen with a positive charge. And so we mentioned that pyridine as a non-nucleophilic base would be useful if we had an acidic hydrogen, which we do here. So the pyridine can remove that acidic hydrogen, and it will do so. Okay, and so now what we have is we have successfully converted a poor leaving group, which is the alcohol, because that would leave as too strong of a base, hydroxide ion. So we have converted this now into a bromophosphite group. And that bromophosphite group, so bromophosphite, is a good leaving group. And so if we have a nucleophile that can do an attack on this, it will. And I have forgotten my hydrogen. That's important. Let me draw that back in. There we go. Okay, because we want to look at the structure of this. And it's important to note that it is a secondary carbon atom, which means that if we have a substitution reaction occurring, it's going to be an SN2 reaction. And so we do have a bromide ion in solution, and that bromide ion can do an SN2 attack. So that means a concerted substitution at this center. And what happens when you do an SN2 attack on a chiral carbon is you end up with inversion of stereochemistry. So if we look at the starting alcohol, the alcohol was on a wedge bond, and it still was here because up until this point, nothing had happened to that carbon center. But in this last step, the bromide is going to attack from the side opposite that wedge, so we'll end up on a dashed bond, and so the answer is D.